Up next to talk about high-speed instrumentation using logic and design to beat performance barriers. Robin Kirk and Chris Ryan. Is that... Hey, Chris. Chris Ryan.
Slight change of person. Okay, I am? Yes, I'm on. I'm going to give this talk from a slightly different perspective as a client of CSIRO. I'm a physicist in a minerals research part of CSIRO, developing analytical techniques particularly aimed at mineral exploration, and then trying to obtain solutions to those problems, tapping into the manufacturing talent here in CSIRO. So in 2004, the Australian synchrotron was about to jump off the drawing board, and we were looking at the design of the X-ray fluorescence microprobe. X-ray fluorescence is essentially raster scanning a sample through a micron-focused X-ray beam, detecting radiation that's giving off, and then reconstructing the 2D or even 3D spatial distribution of major and trace elements, or even chemical speciation, which is a cool aspect of that synchrotron technique. Now, the state of the art at the time was rather less cool, of just a few hundred pixel squared images. And so if we were particularly to go to 3D applications, we want to go to many millions of pixels, so that means a radical rethink of the approach. So we want to do real-time processing in order to get to sub-millisecond pixels, and then also exploit the development, the emergence of detector arrays that have been developed overseas, and put all this together. So that was the concept, but how do we go about doing it? So I discovered that within the manufacturing area of CSIRO, there's this high-speed instrumentation group that has a broad spectrum of skills to tackle problems just like this. So to cut to the chase, a few years later and a few development steps along the track, we have our Maya detector array, 384 detector array, and integrated real-time processing unit, where we can jump from that small image I showed you before to this one, which is 30 million pixels, which also paves the way to 3D imaging. So with 30 million pixels, we can think of going to hundreds cubed for 3D imaging modalities. So the detector development has been a great success, so winning an R&D 100 in 2011, and it's now exported to some of the largest synchrotron labs around the world. Now this success is built on the spectrum of capabilities in this manufacturing division of CSIRO, from hardware, prototyping and integration, fast real-time interfacing through to software development. And one of their key skills is complex real-time analysis, making use of pipeline parallel processing built on FPGAs, field programmable gate arrays. Now, what makes this usually tedious task of programming FPGAs efficient is the in-house development of 3PL language compiler, which gives you a high-level language tool for writing programs for FPGAs. So with this tool, we've been able to implement an embedded form of our real-time spectral deconvolution algorithms, so that we can unfold complex X-ray spectra and produce the images that I've been showing you in real time. Yep. So thank you, and I welcome questions. And being an outsider of the group, I might even call on Gareth Moorhead if you really want to know more about FPGAs. Thank you.
So Chris, Chris, if you go back a couple of slides. What is that an image of?
That's an image of a meteorite sample, and that little red square there is what might have been the state of the art when we started this process. And so to be able to capture a meteorite sample with so much complexity was the aim of the project.
So someone has peered into the innards of a meteorite, or is that a slice of a meteorite?
It's a slice and polished, and then raster scanned at the Australian synchrotron.
All right, hands up, everyone who imagined they were going to see a meteorite tonight.
You never know when they can hit.
I guess one last question from me. What's the, out in the world, who are the sort of most interesting, so synchrotrons? Synchrotrons are a user of kind of fancy FPGA wizardry. Who else uses lots of FPGA, 3PL wizardry?
Well, in prior to this incarnation, the group was using it for machine vision, road crack, number plate recognition, and fast visual processing. Gareth, do you want to add your tuppence worth?
Who's doing fancy work with FPGAs out in the world, other than synchrotrons?
Almost everyone who's got a smartphone. When you reflash electronics, in many cases you're reflashing the FPGA. So the FPGA operates at clock cycle speed to do. Can anyone hear me?
No.
So I was about to say that gate arrays are now becoming ubiquitous technology. They allow you to get the performance of integrated circuits, but with a reconfigurable device, it's much, much cheaper to fabricate, particularly for prototyping and early stage development. So every smartphone has probably got an FPGA in it to do the high-speed part of the analysis.
Paul Graham said, software's eating the world. We're just told now that sort of software and programmable FPGAs are eating the silicon chip world, so that's good news for the software people.
Well, that's sort of part of the answer, but it's sort of replacing circuitry in a sense, and traditionally that's how they've been viewed.
Yeah.
But with the high-level language approach to programming these things, you can think of them as real computing devices.
Yeah.
And so we've implemented our spectral deconvolution algorithms in a way that you might use a traditional compiler language to do it. So I think that is quite new.
Yeah. Questions? Yes.
How much energy and hardware and stuff do you need to make this happen? Could you deploy it on Mars or Moon or something?
Well, it is fairly energy inefficient at the moment and has water cooling in it, etc., etc. But that sort of comes down to speed power trade-offs as well. So we want this to be high performance, and we want it to process 100 million events per second, and so that tends to push the equation to the higher power end. If you're talking about a much lower count rate environment like on Mars and a much space telescope or something, in fact that's where a lot of these arrays are being deployed in X-ray telescope platforms, then the count rates are much lower and you can use different approaches to radically reduce the power consumption.
Question?
Two-part question. The first one is, what are the applications of FPGA outside of research? And the second one is, for software developers who wanted to learn about FPGAs, where can we get the resources?
So let me answer the first part of that question. So the answer, the areas for FPGA outside research, mobile phones, lots of other applications where, traditionally done by silicon chips, now being done by FPGA and programming and other techniques. The second part of that is, where do people learn the software to make these things go?
Well, that's a very good question that I can't really answer because I don't program FPGAs. I'm the sort of I brought the application into the group, and the wizards there use these high-level language tools in order to implement our algorithms.
What's the name of the programming language?
3PL.
3PL. How do I program 3PL?
So I think
What's that? A Google search and
I suggest making
and where do I
with the group.
and where do I get it? Where do I get, like, as soon as he learns how to program it, he's going to want to flash it. So where does he get an FPGA?
The companies that make them, Xilinx and Altera in particular, they release quite inexpensive development boards now, prototyping boards. But these prototyping boards are really quite powerful.
How much is a board online? A couple of $100 and you're doing some crazy stuff.
That make it something useful, and that's where we come in.
Yeah.
What's the name of the boards? Altera
Altera and Xilinx.
and Xilex. And
But,
Xilex.
yeah, Google FPGA.
One question.
It sounds very esoteric, it sounds very scientific, but an example of where this is coming out is in the Kinect sensor for the Xbox. The underlying processing that's going on there with the time of flight and so on, and then the stuff going on with Google with the visual recognition of the environment and so on. All of that is using this kind of technology to process fast enough to get the thing. So even though it doesn't sound like it's incredibly useful, it does find its way out into the processing.
It's inside all the bits. Great. Thanks very much. Thanks very much, Chris. That's great.